We're now going to briefly go through a history of symplectic integrators via a series of important papers in the field. And the first appearance was in the 1950s, in particular in a paper by de Vogelieri. Then there was kind of a dribble of attention paid, not too much, and then serious interest arose again in the late 80s. And then you had a long series of papers, including Feng and Qin in 1987, Channel and Scoville, 1990, Sens Cernan, 88, Wazanian, 88. All of these introduced important aspects of symplectic integration. Many of them are very specific to the integration of n-body systems, and they're all worth a read. We are going to trace through a subset of these and add others that followed. Before we start down that road, however, it's important to point out that we've already introduced something that can give us an integration scheme that is capable of preserving symplectic structure, and that is the Runge-Kutta integration methods. Recall that we can encode a Runge-Kutta scheme via the Butcher tableau, where we have a vector C, a vector B, and a matrix A, and we propagate our equations as xk plus 1 is equal to xk plus our time step delta t times the summation of b sub I, g sub I, where the g sub i's are functions such that each g sub I is a function of x sub k plus the time step times the summation from j equals 1 to s of the elements of the matrix A, aij times g sub j, evaluated at a time tk plus elements of this C vector times delta t. And we've previously established that if A is lower triangular, that translates to an explicit scheme because you never need to be looking at future elements of G to evaluate the current element of G. But if A is not lower triangular, then this becomes an implicit scheme because you do need to implicitly solve these look-ahead functions. In the completely general case, this is not a symplectic mapping. However, in the case where b sub I times a sub ij plus b sub j times a sub ji minus b sub I, b sub j is equal to 0 for I greater than 1 and j less than or equal to s, then the tableau is exactly a symplectic mapping and exactly preserves a symplectic structure. If you stare at this, what this is telling you is that a sub ij for I less than j can't be all zeros. Otherwise, you would be unable to get this summation to work out, other than in the completely trivial case where everything is 0. And therefore, the symplectic versions of the Runge-Kutta schemes must be implicit, which adds a whole level of numerical complexity to their implementation. And so while it is completely possible to use these, they are not the most efficient symplectic mapping. So let's consider some alternatives. And we're going to start with a paper by Ruth from 1983, which posed the question, what sort of scheme can we define in the case where our Hamiltonian h is equal to the sum of a function t of the momenta only plus some function v of the coordinates only? And you will recognize in this a strict split between kinetic and potential energy, with the Hamiltonian being equal to the total energy. We have a potential that is a function of the coordinates only, as we do in systems where the only force is gravity, and we have a kinetic energy term that is a function of the momenta, the derivatives of the coordinates only. In this case, we can define two separate mappings. We can propagate the coordinates q from a time t to a time t plus delta t as q plus the time step times the partial in this t function with respect to p, with p evaluated at the current time step. And separately, we can define the propagation of p as equal to p minus delta t times the partial in v in q, with q evaluated at the propagated time step. And you will notice that this is just a strict application of linearization of Hamilton's equations. Each of these is symplectic, and their composition is equivalently symplectic. So the basic symplectic mapping for this case, where the Hamiltonian can be separated in this fashion, is given by this S mapping. QP at a time t is propagated to QP at a time t plus delta t, with these two being taken in turn. This is a first order scheme, but we can find arbitrarily higher order schemes as compositions of these symplectic mappings. The way that works is we take Q naught to be Q at the current time, P naught to be P at the current time, and then we propagate Q of I plus 1 such that it's equal to Qi plus some constant Ci delta T times that partial T and P, with P evaluated at P sub I, and P of I plus 1 is, again, given by this expression here, with Q evaluated at Q of I plus 1. You find these C and D coefficients such that your overall scheme, this propagation of QP at time t to QP at t plus delta t, matches the nth order Taylor expansion of the solution. And while this is a completely general statement, in practice, it turns out to be hugely difficult to find these coefficients analytically anywhere past fourth order. But this is the basis from which we are going to build up. Our next step in this story is a paper by Neri from 1987, which introduces another bit of mathematical formalism to help us along. Hamilton's equations can be written in a very compact form using something known as the Poisson bracket. In general, the Poisson bracket of a function fg is given by the summation over the n coordinates over which f and g are defined of partial f with respect to q sub I times partial g with respect to p sub I minus partial f with respect to p sub I times partial g with respect to q sub I. You will recognize within this that alternating bilinear form that we've previously discussed. As a notational convenience, we will define this operator d sub g of some argument as the Poisson bracket of the argument with g. If we return to Hamilton's equations, q sub I dot is equal to the partial of h in p sub I. This is exactly the Poisson bracket of qi with h. And p sub I dot is equal to negative the partial of h in qi, which is exactly equal to the Poisson bracket of pi with h. So from this, Hamilton's equations can be written in this ultra-compact form of z dot equaling the Poisson bracket of z with h of z, where z is our state composed of q's and p's as usual. Using our new operator notation, we can also write this as d sub h of z. And we know the solution to the system. Linear system z dot is equal to some operator on z, means that z at t plus delta t is the exponential of delta t times the operator times the initial condition, which in this case is z of t. And I'll pause to point out that this here, this exponential term, this is our symplectic map. This is the operator propagating us from a time t to a time t plus delta t while maintaining our symplectic structure. We now couple this with Ruth's result and look for the case where h is equal to t plus v, and we find that we can rewrite this operator as e to the delta t of d sub t plus d sub v times z of t. And here it's incredibly important to note that in general, dt and dv do not commute. So the ordering here is very important. I can expand this exponential in series, again, matching to an order of the Taylor expansion of the solution. And this becomes the product from I equals 1 to k of the exponential of my c coefficients delta t dt times the exponential of the d coefficients delta t dv plus order of delta t to the n plus 1, where n is the order of your integrator for this particular scheme. So this reinforces this concept of a product of symplectic mappings and means that we can compose higher order schemes out of lower order ones without having to search for the coefficients ci and di for the higher order scheme directly. Our next step is a paper by Yoshida from 1990 on the construction of higher order symplectic integrators. Yoshida defines a second order integrator S2 as a symplectic map for half the time step exponential of delta t over 2 dt times the symplectic map of for the full time step for dv times another half step in dt. The fourth order integrator can then be directly written from this as the second order integrator times some scaling function x1 delta t times s2 times some scaling function x naught delta t times another s2 times the scaling function x1 delta t. So the idea here is that you are alternating between propagation of the coordinates and propagation of the momenta back and forth using various scalings of the time step in order to preserve the overall symplectic structure. In the case of the fourth order integrator, you can set up this algebraic system. X naught plus 2x1 has to equal 1. X naught cubed plus 2x1 cubed has to equal to 0. This again comes from the matching of those coefficients to the Taylor expansion of the system, and solving, we get this value for x naught and this value for x1. In general, the result here is that you can build even order symplectic integrators as these types of symmetric products. So again, S delta T to order n is going to be the product of these two mappings back and forth. So how do we get these coefficients? Remember, one of the chief difficulties here is that these operators in general do not commute. We are aided here by another bit of mathematical formalism known as the Baker-Campbell-Hausdorff formula, sometimes called BCH for short, with one of the earliest closed form solutions published by Dinkin in 1947. The setup for the system is that we have an x and a y that are non-commutative, and we define an e to the z, so this exponential e to the z is equal to e to the x, e to the y. The solution for z is therefore the natural log of e to the x, e to the y, and according to Dinkin's formula, we can write this as this set of nested summations and products. The numerator here of this second summation is given in terms of a set of nested commutators. A commutator, another bilinear form, is exactly what we've seen before. X, y is equal to xy minus yx. So we can nest these commutators like so in order to evaluate them recursively, and that gives us these definitions for the R sub i's and S sub i's as seen in these expressions. So this is not straightforward to crunch through, but it is deterministic and it can be programmed recursively. And so this is something that computers can do quite easily for you. And this is how we can get at those CI/DI coefficients when we're trying to match the Taylor expansion of our solution. As a final step, recall that we are primarily interested in these separable Hamiltonians, ones where t is solely a function of the momenta and v is solely a function of the coordinates. In general, the exponential e to the AD is given by the infinite series from n equals 0 to infinity of AD to the n over n factorial. However, in the case of a separable Hamiltonian, if we think of the higher order operators, say dt squared operating on z, this is the Poisson bracket of the Poisson bracket of z with t itself, which is the Poisson bracket of q dot with t, which by this assumption must evaluate to 0. Prove this to yourself, please, by going back to look at the formal definition of the Poisson bracket and coupling it with Hamilton's equations. And similarly, dv operating on dvz, or d squared vz, is the Poisson bracket of the Poisson bracket of z with v, which evaluates to negative p dot, Poisson bracket with v, which is similarly 0 by this assumption. If we couple this with this infinite summation, it's no longer infinite. E to the delta t c sub I dt is going to be just 1 plus ci dt delta t. And e to the delta t di dv is similarly 1 plus d sub I dv operator delta t. And that means that the propagations of the coordinates and the momenta can be fully separated from one another in the case of these separable Hamiltonian systems. And we define what is known as a drift term, which is the propagation of the coordinates, drift in the sense that we are allowing the coordinates to evolve without touching the momenta. And we define a separate kick term, which is the evolution of the momenta without changing the coordinates. So think of this as an impulse. We are changing the momenta, analogously the velocities of the system, while leaving the coordinates in place. We can compose symplectic integrators for separable Hamiltonian systems, such as the gravitational n-body system, as a composition of drifts and kicks with various scalings on the delta t's, as shown by Yoshida and the rest of these papers. So let's talk about some of the properties of the symplectic integrators built in this fashion. The symplectic mapping describes the time evolution for delta t of a system with a Hamiltonian h prime, which is close to the h of the original system, such that h prime equals h plus delta t h1 plus delta t squared h2 plus delta t cubed h3, this being for a first order scheme defined such that h1 is equal to the partial of h and p. This notation with the subscripts is shorthand for partial derivatives. So h sub p, h sub q, partial of h and p times partial of h and q divided by 2. h2 is partial of h and q squared times the second partial of h and p plus second partial of h and q times partial of h and p squared over 12. h3 is second partial in p times second partial in q times first partials in each over 12. And these particular terms are derived from that BCH series solution. So for a first order scheme, for a time step delta t, what we find is that we are propagating a Hamiltonian, which is very close to the original Hamiltonian h, and the smaller this delta t and the smaller the evaluations of these terms, the closer it is, but it cannot be exactly the original Hamiltonian. H prime is conserved exactly, and in general, H prime for an nth order scheme is H plus delta t to the n, H sub n plus order error delta t to the n plus 1. The key thing here is that H prime changes every single time delta t changes. And that means that the error in the energy, the thing that we are not explicitly conserving with a symplectic scheme, is going to change as well. You can minimize that total energy error with adaptive Runge-Kutta methods, or you can use multiple time-step symplectic methods, or you can use hybrid symplectic integrators. And we're going to cover each of those in turn. But first, let's talk about the simplest symplectic scheme that you can build. And that is known as a leapfrog or velocity-Verlet integrator. This is explicitly applicable to separable Hamiltonian systems, and it is a scheme where you are propagating the coordinates and momenta independently with one another and offset by half a time step. This is a symplectic second order scheme. You propagate the coordinate to a half time step later, so qk plus 1/2 as q sub k plus delta t over 2 times the partial of your Hamiltonian with respect to the conjugate momenta, evaluated at the current value of the momenta, p sub k. So this is your first drift. You then propagate your conjugate momenta, your kick a full time step to get p of k plus 1 is equal to p sub k minus delta t times the partial of h with respect to p, evaluated at the drifted coordinate, q of k plus 1/2. And then you drift the coordinate another full-time step to continue that offset to get q of k plus 3/2 is the previous value of q sub k plus this same propagation, now evaluated at the propagated momenta. And you keep going with this. So you continue for as long as you need to, and at the very end, if you need to synchronize the two values, you just propagate the coordinates another half step or propagate the momenta a half step in order to get both your coordinates and your momenta to be aligned in time. In general, if we have a system of differential equations of the form x double dot is equal to f of x, which you will recognize exactly describes our gravitational n-body system, we know that we can write this f of x as negative the gradient of some scalar function v in x. And we have an energy function where, like our specific energy, it's 1/2 of x dot dotted into itself plus this v of x term. Then we can implement this scheme as x of I plus 1 is equal to x sub I plus the derivative of x dot I plus 1/2 times delta t, and x dot of I plus 3/2 is equal to x dot I plus 1/2 plus the second derivative of x, which is this function f of x evaluated at x of I plus 1 times delta t. We can automatically build in that half step offset and create equations that automatically align this without losing that leapfrogging structure. And that has this form. So most typically when you are building yourself a numerical integration scheme based on velocity Verlet integration, you will implement something like this. So this integration scheme, simple as it seems, is incredibly powerful because it has that symplectic property, because it will automatically conserve the symplectic structure. And if you use small fixed time steps, this will also do a shockingly good job of preserving the total energy of the system. However, as soon as you start modifying delta t as you go along, and as soon as your step size grows too large, then all bets are off. And the energy of the system that you're propagating will start to drift quite rapidly away from the energy of the original system. The other neat thing about this scheme is that it is fully time reversible. You can run time forwards or backwards. Delta t can be positive or negative, and nothing much will change here. That is not necessarily true for all symplectic schemes, and definitely not true for a lot of the implicit Runge-Kutta schemes.